The reason for this video is I recently saw a great deal on eBay. Picked up a box of 10 security cameras for 20 bucks, including shipping. And when they arrived, I plugged them in, and of course I couldn't use them because they're password protected. So what this video is aimed at is I'm going to take you through my thought process and the way I bypass the security on these devices, and hopefully I can help you out if you're looking at embedded product design or how to analyze and maximize or expand the use of embedded products you may have lying around at home. I'm just going to log on, and I know the IP address because I've logged onto my home home router, and I've found where the IP address is assigned. I'm going to type in the yep, there's the home page, and you can see this little login, and I'll try all the common passwords, all the root, Tor, common Linux, bypass, and nothing works. Okay, I'm going to go ahead and load my Pi image on a fresh SD card. Just chuck that in my reader. I know I kind of went through that fast, don't worry too much about what I did there. I just chucked a new image on the card and loaded up, and when it prompted me I just updated the factory settings. The only extra step I did was just enable the VNC viewer, and that just gives you the screen capture screen that I've got now, so you can sort of follow along a bit easier. The first thing I'm going to do is just load a whole bunch of programs. I don't know how many I'm going to use, but just programs that are definitely going to be helpful for sort of hardware interrogation. So the first one is Nmap, and I'll just go ahead and load that now. What I like to do is just check that it did install by just hitting the command. Okay, the next tool I'm going to install is Flashrom. And Flashrom is just an EEPROM read writer, and good thing about this is that you can use the pins that are native on the Raspberry Pi, so you can literally plug an EEPROM memory chip straight into the Raspberry Pi. There's a few dependencies, so I'm just going to install these first. The next program I'm going to install is binwalk, and that'll let us decompress any binary images or firmware. So I'm going to go ahead and install that. There's a couple of dependencies as well, so I'm going to grab that off GitHub and install it. I'll just make sure bin walk works. Yep, and we've got our options, so it's installed correctly. Right, that's probably all the software tools we need, at least for the moment. And we're probably ready to start looking at the camera. Okay, the first thing I'm going to do is just run an Nmap scan on it. Cool, and this does take a little while. Once again, we're doing a full scan at the moment. Depending on what you're doing, it can take a little or a long time. We're running a full scan, which is going to check for any open ports and hopefully provide a little bit of detail about the server that's on the camera and what it's actually doing. But you'll see we saved it, actually saved it to an output file. So if I want to recall any of the results from the scan at any time, as long as I'm in the folder, I can just output the contents of this capture file. And yep, there we go, whenever I need to review it. So I'll just scroll up here and go over a couple of little things. So it's reporting 995 closed ports. However, these ports, so port 80, port 443, 554, these are all open. They're still secured, but they are a possible method of entry. It is running a server on port 80 HTTP, which is BOA 0.94.14. So BOA is the name of embedded Linux server. It's a little bit older now, but still a couple of products you'll see every now and then. And port 80 is serving this web page, and because you'll just recall, if we jump back, go to the home page of our camera, and yep, this is the web page that you're getting on port 80, which makes sense because we're not authorized. Unfortunately, I did Google this version, and there is a couple of exploits to get past the login screen, but they're I can't remember the version, but it was a couple of versions lower than this. However, by the time this 94.14 server came out, this has been patched, so those exploits no longer work. Otherwise, that would have been a possible way to get access. If we look further down, we'll see port 554 RTSP. So I think that is real-time streaming. I don't know, sounds right, go with that. But that is a video stream, so it is broadcasting live video on port 554. They typically do still require a username and password, but we'll definitely come back to look at that as well. 843 open. Yeah, we're probably not going to have much luck with that, to be honest. Same again, port 8080 is another secure port. So yeah, you may be able to get access through exploiting some of these ports. To be honest, I don't know how. This version being the patched version, it's probably beyond my abilities. But if you're that way inclined, yep, you could definitely look further into that. Okay, I'm going to go ahead and just open this camera up. So obviously, first disconnect power. There's a couple of Phillips head screws in the back. Okay, it looks like I'm going to just take these Phillips head out as well, and there's an infrared LED front PCB, and that just simply, you see in the second, plugs into the back PCB, but we can just remove that because it's just a couple of header pins connecting them to. Cool, once those screws are out, pull that off nice and straight, and you'll see that connector just had a couple of header pins up there. Don't know how easy that is to see. A couple of header pins connecting the boards anyway. I don't really need this board at the moment. It's not really serving the purpose for the rest of this video, so I'm just going to put that to the side. But you'll see the main board. What I'm going to do is just take out these couple of standoffs so I can pull the board right out and have a proper look. Cool, and I'm just going to take that out, and there is a RF connection to the back. I might just go ahead and just be careful when you disconnect these. They're quite easy to damage. Obviously very small. You just need to get a bit of leverage on the right angle and pop it off. Okay, that was kind of interesting. I mean, this is your typical embedded device. It's single board. There's a bit going on here, but if you break it down, you can kind of see, make it out a bit easier. So we've got the camera on the front, obviously, and every now and then you'll turn the camera on and you'll hear it click. It'll make a click, 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 click. And what I think that is you'll see this big back end plastic on the camera, and that's the IR filter. So what that does is during the daytime, there's an IR filter which covers the lens, which just lets obviously visible light through the camera, and all the IR is filtered out. However, at night time, you actually want to maximize your IR input. That's why obviously the IR LEDs on the front act as a bit of a floodlight. But the IR filter that's required for daylight will actually block out a lot of the light that you want at nighttime. So there's a physical disc, and there's a little, I guess, solenoid or something, and that will mechanically move the IR filter out of the way and let that light through. And you'll hear it adjust its settings when it goes through night and dark. It'll make a clicking sound, and that's just the IR filter moving in and out of the lens. And I'm guessing these two solid wires are probably the power for the solenoid to drive that filter. Couple other little things. We had a header pin that the lights were connected to. There looks like a crystal there. Down in this section looks to be the power supply or the regulators, and you can sort of tell just with the coils and the bigger caps that we use for smoothing. There's a small crystal again just below the camera. LED, yeah, looks like a little multicolored LED, a couple of transistors. Not too much more going on really. We'll flip it over. Okay, on the back, yeah, we've got our Wi-Fi card, and that's just simply, once again, just unplugs a couple of header pins. We can actually take that off for now. Our reset button, and okay, so this Mozart 330, I'm not entirely sure what that is. It definitely looks like the processor, whether that's a FPGA or some sort of CPU, I'm not entirely sure. This looks to be a RAM chip. Little battery for probably a real-time clock or some sort of RAM backup. There's an SD card position. However, this model does not have the SD card ability installed, with all that missing. And alongside that is a little, I guess that's probably the SD card controller chip, which is not required. Okay, so this is very interesting. There's a little header which was not connected to anything. Now, typically you'll find in embedded products, this is either a UART port or some sort of diagnostics or factory programming. Best case scenario, what we want is this to be a UART. UART simply being a logic level transmit and receive that will give us information straight from the operating system and possibly the ability to give information back over a serial terminal. Also, another interesting one, I'm just going to peel that OK sticker off. If I can get that. Okay, what I can see is MX25L64, and it's a bit scratchy, but it looks like 06 or something. But I happen to know that this is a reasonably common serial EEPROM chip. So that's going to store probably the firmware on it. And I know that our Flashrom program can read this, and all we need is a Raspberry Pi and just a way to connect it to the Raspberry Pi. So that's quite interesting. I'll just bring up the data sheet for it. So here we go. Just on my Macronix, yep. So MXIC, this is the chip we're looking at here because I can read that on the board. Have a look down. It's quite a big file. You're really just skimming to pick out the key points, but serial flash and 64 megabit. So 64 megabit is, remember, 8 megabytes. And here's some common packages. So 16 pin, so it's the 8 pin package, SOP, but it doesn't look like that one. It's probably this one here. And I actually have measured it with calipers, and it is this 8x6 millimeter. And we've got our pins here, 1 through 8, and a quick key and what they are. Being chip select, data in, write protect ground, data out, the clock, hold, and VCC. So these data in, data out, and clock are all common to SPI devices or flash memory devices. Block diagram. I mean, the key information you really want is just the pin out and that it's 8 megabyte. It goes right into the operation, memory addresses, read and write cycles. But yeah, we won't go too much further into that because I know with these pins here, this pin out is enough for us to be able to read this using the Flashrom program. Hardest thing is this being sort of a SMD or surface mount device is being able to actually connect that to our Raspberry Pi. And without some sort of adapter, I mean, you're never going to solder wires onto there. You'd just be driving yourself insane trying to get that. So unfortunately, I don't have an adapter ready to go, so I'm going to have to make one. I've got the board just in the workshop, and what I'm going to do just before I desolder the flash memory is I'm just going to try and interrogate this port, which we suspect is a UART. The way I'm going to do that is it's got 4 pins, so I'm just going to draw a rough diagram. I'm just going to say I've got the power Ethernet port and another port just to give me some orientation, and then we've got the port up here, and we've got 1, 2, 3, 4 pins, and I'm just going to go through, and as I figure them out I'll just note on my paper. So the first tool I'm going to use is just plain old multimeter, just a continuity checker. So I've got my probes here, and you should just hear it. Yeah, so when we get continuity, we'll get the tone. Now, the first thing to do is probably find a known point of reference on the board that I can compare it against, because the 4 lines we're looking for are ground, power, transmit, and receive. Now, ground should be pretty obvious, but transmit, receive, and power all have a voltage on it, depending what state they're in. So they can be a little bit tricky. So the best thing is to find a known point. And for this, I do already know a point because I've looked up the data sheet for the flash memory chip. And I know that pin 4 is ground. So I'm going to chuck my probe on pin 4. And I'm firstly just gonna try and confirm this by touching a known ground point where any one of these exposed copper pads. Yep, and that's showing I am grounded. And now I'm just going to go through these 4 pins. Okay, so that top one is showing 0 ohms. Yeah, and always pays to check the rest just in case you got something wrong. But it definitely looks like that top one is our earth. So on my paper, once again, I'm just going to draw off an earth. So I know that the top one is earth. Right, next, another known point. I also know from the data sheet again that pin 8 on our flash memory is VCC, or supply. So I'm just going to put a probe on pin 8. And once again, go through the 4 pins. And just double check them. Okay. Yep, that bottom pin looks like it is supply. So I'll just annotate that. Yep, so we have our supply and our earth. Now it's just these 2 middle pins. One's going to be transmit and one's going to be receive. It can be a little bit tricky to figure out which one's which because the voltages vary, and you might struggle to do this with an ordinary multimeter, but what we really need is a logic probe. And I actually have this multimeter. It's about, I don't know, 30 years old. It's hanging in there though, and the good thing about this is I have this logic setting. So it turns the multimeter into a logic probe, and what that's going to do is give us a very fast response time between 1 and 0, or 0 and 5 volts. Should actually do the newer 3.3 level logic as well. So anything over about 2.5, 3 volts, it'll give us a logic high, and anything below, it'll give us a logic 0. And it's got a very fast response time that a normal multimeter just won't catch. So you really struggle without one. What I'm going to do is connect the earth just once again to that exposed pad. I'm going to plug in our board. Now it's not powered on, it's not connected at the wall. You really want to minimize touching this board when it's powered up. The resistance in your hands, especially across these small surface mount devices, you can do a lot of damage when power's applied. This is actually the second board I'm using for this demo because, yeah, I blew one up by touching it. So avoid as best you can touching it when it's powered up. Okay, I've got it set up. I'm just going to apply power now. Once I apply the power, I'm just going to probe these two middle pins, and I'm on the logic setting, and you should just be able to hear the data. And what I mean by that, you'll see in a second, is you'll hear it, the ones and zeros ticking very fast when you're on the transmit pin, because it's spewing out a whole lot of diagnostic data. So the board's powered up. Try top one. Yep, so you hear that sort of regular, sort of coming in waves. The beeping, that's logic data being pushed out through the transmit. And it'll probably only get to a certain point when it reaches a boot screen or something. So I'll just reset it. Reset it there, and I'll try the other pin. Yeah, and that's just high. So that's receive. It's waiting for data to come in, and there's nothing. Chuck it back on the top, transmit. Yeah, and I'll just try and show you what I actually mean. Not sure what that's going to look like, but I'll chuck it on the top pin. Oh, sorry, I just need to reset the board again. And each time I reset the board, it's kind of got the same pattern. It's beep, beep, and then a whole bunch of beeps, and then, so I know it's sending out the same data each time. So it's another good sign. It is actually a UART port with the transmit pin. Okay, board's powered down at the moment. Last thing I'm going to do is actually try and get the baud rate. So when I plug it into a PC or the Raspberry Pi, it's just going to minimize the amount of settings I have to go through. And the way I'm going to do that is, let's see if I can get this. I'm just going to hook it up. So firstly, the way I'm actually going to connect this, you'll notice that this header is actually very small, and it's smaller than any of the connectors I had lying around. It's, I don't know, some sort of micro JST port or something. What I actually ended up doing was I've got a couple of broken MacBooks lying around, and I pulled out one of these speakers from one of the MacBooks, and on the end of that is a very small 2-pin connector. So we'll write down on our paper. Once again, we now know the top pin is transmit, and the bottom pin is receive. Okay, so we've got our transmit and receive pins. So I'll get this MacBook connector, and all I need to do is plug it into the 2 inner pins. Just like that. Because we have our earth on the outside, which is just connected up to this bare metal exposed pad, and transmit and receive, we only need the 2 pins, being the inner pins. We don't need the power because whatever device we connect it to, the Pi already has its own power. And just from memory, I think the flash memory chip is 3 volts, 3.3 volts. And we know the power pin is directly connected to this header, so we know that whatever we need to interface will probably has to be 3 volt logic level, which conveniently the Pi is. Okay, to figure out the baud rate, I'm going to plug it into my scope, and just see if I can pull up the data stream and grab the frequency, and then we'll know which baud rate to chuck in our settings when we try and connect to it. So it's pretty simple. All we're going to do is just, once again, connect the earth up to our scope probe, and then this probe conductor, I'm just going to connect to a transmit. Power up. Just try and zoom up so you can see a bit better. Cool. Okay, I'll just turn the voltage up. Yep. I'll power it on and just make sure we're looking in the right place. Yeah, looks like I just need to adjust the time a bit. What am I on there? 25 microseconds. Okay, so at this point, normally on a digital DSO, digital storage scope, you can just set the trigger levels and hit a single shot to capture. Unfortunately, the scope took a bit of a beating a while ago. I had mains voltage put through it. And it hasn't quite worked the same ever since. So I just need to manually try and capture this data stream. So I'm just going to reset the board. And when I see it running, I'm going to hit stop. No, missed it. I'm trying to guess it. No, missed it. I'll just reset. Oh man, it's frustrating. Yeah, got it. Okay. Yep, word of warning, don't use imported Chinese soldering irons without an earth pin, especially with the MEN earth system. Because that's what I ended up doing, and I got a back loop through the earth, through the circuit board and through the earth probe, which was still connected to my scope. So blew up the meter, blew up the board, and yeah, it's done some damage to my scope. Anyway, moving on. We've got the data stream there. I'll just expand that a bit with the timescale. Cool. If you've got a digital scope, hopefully you can bring up some automatic settings. But you can do this on an analog or whatever. I'm just going to bring up some manual cursors. If I can remember how. Channel 1. Yep. Cursors. And manual cursors. Cool. Okay, what I'm going to do, I'll bring this across a little bit so I can see just a single one as in a logic high. So there's a good one there, and I'm just going to move my cursors onto it. So I know that this one clock pulse, or this one, it's not really a clock, this logic high is going to be transmitted at the baud rate of the port. Change my cursor. Yep, and you'll see up the top as I'm adjusting these cursors, it's just manually adjusting the time period between them, and then it's calculating the frequency, which is just 1 over the time period. Cool, so maybe even, I'll expand that out a little bit. Might be too much. There, so let's try and maximize our resolution. Put that right at the start of our measurement. Yeah, and I'll try this right at the end. Okay, and you'll see there 36 kilohertz. If you just look up the top, 36.76 kilohertz. It's not dead accurate, just the scale and the resolution that I captured it at. If you want to get a bit better, you probably need that trigger to actually work on your scope and you can grab it. But 36 kilohertz, so if we look at the standard baud rates, 9600, 2400 or something, all the way up to 100 and whatever it is, 111,000. They're all standardized baud rates, and one of the baud rates is 38400 or 38.4 kilohertz. And we can see there 36, yeah, it's pretty close. I think this the transistor logic UART specs has it within 10% to still effectively transmit data. But yeah, I think you'll find once we plug it in that the baud rate will be 38400. Okay, we're ready to grab our flash EEPROM. I'm just going to take it off this board and chuck it on the little adapter we made. And then we should be able to plug it straight into the Raspberry Pi. So the way I'm going to grab it is just chuck a bit of flux, and then I'm just going to use a hot air solder gun to remove this EEPROM chip. What the flux does is primarily it cleans the board, so it cleans any impurities or oxidation as it heats. You have to have a very clean surface for the solder to stick. But secondary to that, it allows transfer of heat, and you really want it to start flowing, get under your chip, and really transfer that heat all around, which is you'll find is really critical, especially for these surface mount components. Oh man, so just with that camera on the underside, it doesn't really sit well, but let's see if I can pull this off. Just that angle was quite hard. Probably used more heat than I should have, but I think we're alright. Sometimes it's better to just try and go for it rather than stop start. But you can see one of the reasons why we had to use so much heat as well is that big heat sink on the underside. Okay, the way I'm going to solder this to my board, a little prototyping board we made, is just power up my soldering iron. Okay, so a lot of factory-made products use lead-free solder, part of the RoHS restriction of hazardous substances, RoHS. You'll see that little RoHS sticker on a lot of products. It means the solder is lead free, which, yep, great for the environment, but absolute mission to try and solder with. So the first thing we want to do Give me a second. Yeah, so one of the reasons it's quite hard to solder is because it's got a higher melting point. So the best thing to do is lower the melting point of the solder by mixing in some lead-based. And all the lead-based stuff is just your normal sort of hobby lead tin mix. So if you mix that in with factory stuff, you'll find it just lowers that temperature melting point. It'll make it a lot easier to get this on and off once we're ready to. So I've mixed in a bit of my own solder. I'm just going to try and now get it off this heatsink pad because I really don't want to have this pad sticking to our test board, because that would just be a hassle. Just use some solder wick, get that off. Yeah. And just on these little pins, pads, I'll just make sure they're tinned. Yep, so they're tinned. Nice layer of home hobby solder. And I'll just clean it up with a little bit of isopropyl. And once again with our prototyping board, I'm just going to tin that with a bit of our solder. Now, the key to solder is you really don't want too much. It's always less than you think you need. But especially with these homemade boards, they can get a little bit tricky to solder because without the solder mask, the heat and the solder tends to flow down the tracks, and you can find you just keep pouring solder on and it will just flow down the tracks. And it can be hard to judge how much. I'm just going to put a little bit of flux on, just so it sits nicely, transfers that heat. So you can see where the camera manufacturers have made this. I've tagged this chip with a yellow dot, and that will be our pin 1. So I'll just try and line that up as best I can. It's not too critical. You'll sort of find that once I heat this, it will suction almost towards the pads as the solder starts to flow and they grab onto their pins. And that's that. So hopefully we've attached our chip and we've got this nice standard pin out which we can just plug straight into the Raspberry Pi. I've just connected the ROM chip up to the Raspberry Pi, and the way I did that is I went back to our data sheet for the chip, this MX25L6406E. Scroll down to the pinout. Found our pinout, this 8x6mm, and I just went through these pins. So you recall this number 1 pin was the yellow dot that was put there. And I just went through, so this number 1 will be chip select. I went to the Flashrom website, which is a program we're going to use to read it. scroll down to connecting and chip select, and it's telling us chip select goes to pin 24 on the Raspberry Pi. So I just googled Raspberry Pi pinout and I counted across to 24 and connected chip select. And then I'll do that for all 8 pins. So pin 2, SO, SIO, which is serial data in, because we've got our little legend here. Back to Flashrom, DI or data in, pin 19. Once again, found pin 19 and connect serial data in. Write protect. So just watch this one here. It's telling us write protect, hold, as well as VCC or power all need to be connected to 3.3 volts. If we look across at the Raspberry Pi, there's only one, correction, there are two 3.3 volt pins, but we obviously need to connect 3 pins to it, being our supply voltage, hold, and write protect. So that's the reason you might have seen just in the, when I was connecting it up, the little breakout board, just so I could split this off 3 ways and connect write protect, hold, and VCC all to 3.3 volts. Ground, yep, self-explanatory. Any one of these ground pins will do. Clock, a clock being pin 23, and hold and VCC, once again to our supply voltage. Okay, once that's all connected up, hopefully you've done it right, and I'll just bring up our Pi again. Okay, the command to actually read the Flashrom, I'm just going to make sure I'm in my folder again, my projects folder, which I am. First thing we need to do is set up our interface, and we just do that by going into our configuration settings. And just make sure that SPI is enabled. If that's not enabled, you're going to have issues. And yeah, no need to restart your Pi. You can just go back. Okay, we should be good to read our Pi with, read our chip with Flashrom, which is the program we installed earlier. And the settings for this is just to set our programmer. I'm just going to lower the clock speed because I found it has higher success rate with a slightly lower speed. Minus R, we're going to read it, and I'm going to save it into a file, and I'm just going to call that camera 1. Okay, we need for this chip in particular, we need to set, tell it what kind of chip it is, and it's a little bit long, but it is the MX25 capital L 6406E / MX 25L 6408E. And I'll chuck verbos. Enter. And hopefully, if it's all connected right, it should start reading the flash. It took a little while, just with the lower clock speed, but I do find it's more reliable. And just to also increase, or sort of decrease rather, our margin of error, you'll see I did it 3 times. And then the reason for that is we now have a safety net. We have 3 memory dumps from that chip, 1, 2, and 3. And just to make sure that they're all the same, I'm just going to run a MD5 checksum on them, which will be OpenSSL MD5 and then just the file name. And I'll just do this for each of the files, and I know if they're all the same, then it copied it correctly every time. If there was one checksum that was different or a discrepancy, then I would know that my cabling's not correct, or some interference, or a loose connection, or something's not quite right. But obviously I can see there that it's run the MD5 on it 3 times, and all 3 times it's come back with the same hash. So I know that 100% I have downloaded that memory correctly. I'm ready to put the memory chip back on the board because I've taken the dump off it, and now I can keep working on the board as normal. Instead, what I thought of putting the original chip back on is I've actually found the same chip but a slightly bigger package, and this is actually off I think an Apple motherboard, but it's the exact same chip, same model number, everything. It's just in a larger package. And what this means is if I place that back on the board instead, I've got this Alligator Easy Flash memory chip connector. I can just plug this straight onto the board, and that way I can have a play around with the firmware. I can change the files, I can change settings from my PC, and I can just quickly upload it without having to desolder the chip every time. It's going to make life a lot easier. So I'm just going to go ahead and solder this chip back onto the board. I've got the chip soldered back on the board, the larger chip, and all I'm going to do is, because obviously it's got whatever memory was on there last off the Apple motherboard, I'm just going to unplug this connector we made and plug in this alligator clip. And I'm simply going to connect this up to the chip, make sure that's lined up. Cool, so we're plugged onto our memory, and I'm simply going to write back one of the dumps we took from the camera back onto this chip. And all I'm going to do is the same command, but instead of read, we're going to write. And hopefully this should put the camera firmware back onto that chip. Okay, we've got our Flashrom programmed back on the board, camera boots. Next thing to do is connect our serial ports together. The way we're going to do that, if you look over here on the Pi pinout, you'll see all the pins. You'll see GPIOs 14 and 15, but underneath that they also double as a UART, or double as a serial port. So pin 8 being transmit and pin 10 being receive. Obviously the receive on the Pi is going to connect to transmit on our other board. So I'll go ahead and connect that up. What I'm going to do is just plug in my little Apple speaker bodge cable, just to those inner 2 pins. And I know that my red wire is transmit from the testing I did before. So I'm just going to go ahead and connect that to pin 10 been received on my Pi. And we know from looking at the schematic of the flash memory chip that was 3 volts, which is connected directly to a header on the board, so we can assume our serial communication is 3 volts, which the Pi is completely fine with. And I'll go ahead and connect my receive wire to the Pi's transmit, being pin 8. And lastly, we just need a common reference, and that's just our ground. So I'll connect the ground pin on the Pi, and I'll just bring that over and connect that to this exposed metal shield tab on the board. Cool. It looks like we're almost good to go. Not powered up yet, but I'm just going to get that ready. Cool. Okay, we'll flick back to our terminal on the Pi, and the program we're going to use to communicate is just Minicom. So I'll go ahead and install that, and I'll spell it right. Cool. So Minicom is just is quite a universal serial transmit and receive program. Firstly, before I run it, what I'm just going to check is, once again, under my configurations, interface. Now what you're looking for here is you want to go down to your serial, and you probably want to disable your serial shell over login, because what that does is it sets a serial shell up, or sets the Pi up for serial communications at boot, and it outputs a whole lot of data over those ports. But I don't want to use those because it can kind of interfere with what you're trying to do if you're trying to use a port for other things. So I'll disable that. But yes, I would like the port enabled. Okay, and I'll exit out of there, and I'll go ahead and run Minicom. Okay, the first thing I'm going to do is Control A. After I hit that, it doesn't look like anything, but we're in a kind of a hotkeys menu. So now I'll push Z for my options, and I'm going to go O configure, and just come down to serial port setup, and I'm just going to make sure that that E is the correct settings, which it looks like it already is. Just from our testing before on the scope, it was about 36 kilohertz, and then that option there is 38.4 kilohertz, or 38,400 baud, which is what we expect to see data on. So I'll save that again, and yeah, I'll just save that as default, even though I think it already was. Alright, I'll exit out of that. Okay, at the moment we should be live in our serial terminal, and the way I'm really just going to confirm that is I'll add a couple of keystrokes, and it looks like we're getting data back. Now, because I'm connected to my board, that's why. I'm just going to go ahead, disconnect that, hit a couple of keystrokes. Okay, so this is what you should expect to see when you're not connected, is no feedback. A good test to do with your serial connections is just to short them out. So I'll just go ahead and short these 2 wires straight from the Pi, transmit and receive, and hit a couple of keystrokes. And there you'll see on the screen that it's receiving straight back what you're transmitting, which you'd expect to see straight out the transmit, straight back through the receive. When your wires are touching, break that connection. Yep, and it no longer receives. So it's always a good go-to first thing to just check your serial program is actually working. Just short those pins out and make sure you get that loop back on the data. Right. So I know my port's working, I know I'm live, I'm going to connect that back up again. Okay, pretty happy with my connections. I'm just going to go ahead and power up the camera. And there, looks like we are receiving serial data. Excellent. Okay, well, it's quite a lot there. I'll scroll back up to the top and we can just see the very first things and just have a look if there's anything useful. It's just a Linux kernels and operating system loading. Okay, here we go. So very first thing, we can see our flash, SPI flash configuration, 8 megabytes. And that's the chip we desoldered and reflashed, which we would expect to see 8 megabytes. So it's nice to know the system's recognizing that again. Come down further. MAC address, I don't know, might come in useful. Mozart 330, that was the name of that CPU or FPGA, whatever it is, on the board. Okay, down a little bit further, image name. Okay, we've got an actual Linux distribution, 2.6.28.9. So you could, I don't know, you can maybe Google that, see if there's some exploits or vulnerabilities for that version of Linux. And it's an ARM, so it's running on an ARM architecture, which funnily enough, the Raspberry Pi is also ARM. So you could expect that if there was any executables on this device, you could probably extract them and run them straight on the Pi with very minimal mucking around. Okay, down a little bit further, and yep, it's starting to load the kernel. Okay, this line here, that's we're going to copy them. We're going to copy that for now. I'm just going to go copy. Yep. So that's setting the initial conditions for how to find its file system and where to boot to. So the root device is MTD block 1, file system type squashfs. So squashfs is a read-only file system. It's quite common on embedded devices, just to stop users overwriting any files or changing the structure, rendering the device unusable. So it's read-only. We'll scroll down further. Okay, this is just all, a whole lot of stuff it's loading. Wireless driver, looks like that might have been that module we pulled off right at the start. Another wireless driver. IP addresses. Okay, that's our IP address there. .35 is what is on the local network, which is the web page we went to before. There was one more thing I was looking for, and I probably missed it somewhere because there was a lot going on. It was basically, here we go. So we have one serial flash creating 4 MTD partitions, or I think it's memory technology device or something. What that means is MTD is a way of partitioning flash storage. So this is on the one chip, but it has come up with a partitioning system. So it effectively has 4 drives, being the bootloader, the root file system, squashfs, and there's 2 file systems here, JFFS2-1 and -2. So these are probably user configurable. That'll be anything the user is allowed to change, passwords maybe, I don't know, but there's 2 file systems that the user can change, but you'd expect the majority of our firmware to be located within this root file system here. Okay, we'll just go right to the bottom. Okay, and it's given us a login. It's a bit messy. I'm just going to hit enter. Yeah, and just clear that again. So, I mean, once again, you can try those sort of default passwords. I have tried a few, yet nothing really works. But at least it gives us a login shell. Another one, yeah, that root ADC video. I don't know, someone said that worked. I couldn't get it to work. No, okay, we are stuck at the screen, but we do have some sort of a shell. What I'm going to do is cycle the power. I'll scroll to the top again, and you'll notice right at the very first section, hit any key to stop auto boot. And here's a little countdown timer. So it's given us an option to stop from here downwards, and we can stop at the bootloader if we hit a key. So I'll try and cycle the power. We're going to restart it, and we're going to try and hit a key. Depending on what that timer is, it may already be set to 0 and skip straight past it, but if it actually gives us a countdown, we can hit a key and try and stop it there. So I'm just going to cycle the power. No, I've missed it. I don't know what I've done there. Cut the power, cycle again. Yep, spacebar. Ah, bugger, missed it. Okay, I'm gonna cut that. Cycle the power. Ah, man, missed it. Really? Maybe I'll try a different key, not spacebar. I think I know what's happening. I think the lag between the VNC terminal is too slow to catch it. I'm just gonna hit the keyboard on the actual Pi itself. I've got that running on another desk. Cycle the power. No, I actually did miss that. Bad day. Okay, got it. Yeah, so actually I can't do that through the VNC. There's too much lag. Okay, U-boot. This is the bootloader, and it's given us some options. There's actually a couple of options that are built into Linux to let you reset a password, funnily enough. Now, if you want to know a couple of commands, you can enter at this. You're pretty limited, but type help, and it'll give you a couple of little options. What we're looking at is the set environment variables. So we're going to change them slightly. We'll set the boot arguments, and I'm just going to paste what we copied before. So those are the initial boot arguments that it's expecting and that run normally. I'm just going to tack on one to the end, and I'm going to say initial condition equals shell. So when it runs this, it's going to boot as normally, but instead of going to the password, it's going to run a shell and hopefully give us access. Okay, that's saved. I'll just hit boot. Yep, and it's given us a shell. So we are a little bit limited because it hasn't finished the full boot script, but hopefully it's enough to change a password. And you can see here, who am I? Yep, I'm root access. Okay, so you can see there is one root account. There's a password. It's a MD5 crypt password. So I mean, you could try and hash that, try and crack it, but depending, I mean, if that's a MAC address, you'd probably be there all day. You'd really only be lucky if it was a short 4 or 5 long password. So I'll just exit out of that, and I mean, I don't really need to change it. Crack it. All I need to do is just change it, and I'm just going to simply do that. By entering my own password. Can't update. Read-only file system. Okay, so if you look here, I'll list the contents of this folder. So we're actually in the squashfs file system. And if we look down at this password file, it's just a link, and it's linking us to Flash, which is another partition and password. And you could hopefully assume that all these links going to the Flash system, that Flash would be the read-write partition. So all these files here that are the actual file, they are safe in the squashfs, they can't be written, but all these links are made to be written. The reason we can't write it is because it hasn't completely finished its boot process, and for some reason it hasn't loaded the JFFS2 file system correctly. But what I can do is just try and remount the Flash system. Okay, looks like it accepted it. Give it another go. Password changed. Yep. So it's just a matter of remounting that rewritable partition. Password for root's changed, and we could probably even try just to confirm. And just from memory, that hash does look different to what I saw before, so it looks like it has updated that on the read-write file system. I'm just going to exit out of that, and I'm just going to cycle the power because I have a root password saved, and this time I'm going to let it do its thing and completely load its settings correctly. You'll find that if you don't have a Ethernet cable plugged in, that you will keep getting a request to join a network, and it will bump you off your when you're trying to type commands. It's quite annoying. So the way to get around that is to just plug an Ethernet cable in and supply an IP address to it. It will stop those annoying prompts to connect. Does take a little while to boot. Okay, so login screen. I'm just going to hit enter, get rid of that. Login. Okay, root. And I'm just going to type the password I just entered. Yep, and we have show access as root. Excellent. Unfortunately, if we jump back to our login page, we do not have access to the HTTP server, and the reason for that is because if we jump into this directory here, I'll explain this a bit more later, but the password for the login screen is the SSAPIV520 folder. Yep, so that's the hashed password for the login to the web server, and it's actually some sort of proprietary Vivotech hashing algorithm. So you can't even attempt to crack it because it's, well, anyway, I couldn't figure out the method used to hash it, and so there's no way to crack it without knowing the details. There is a workaround, and we'll get to that shortly, but yeah, in case you're interested why you still don't have access, it's because that's where the web server password is stored. Okay, so how do we go about getting the web password? Well, there's no way to crack it. It's a proprietary hash, and as far as I know, you cannot crack that password. What we can do is, we've just about hit the limit with where we can go on the camera itself. So I'm just going to exit out of Minicom. Yes, and I'm just going to shut down the camera for now because I don't need it. What we're going to do is jump back and have a look at this firmware. Okay, so the reason I went through all the hassle of building a circuit board and extracting it, extracting the firmware directly from the chip is I could not find this specific camera. I could not find the firmware anywhere on the internet. As fast as the internet is, for some reason, this particular model, I could not find the firmware. I think alarm.com updates them remotely, so the firmware is never actually sent out. It's done over TCP or something. So the actual file itself is not really available to end consumers. So that being said, that's why I had to extract at least the binary from the chip. But that's okay. That's exactly why we downloaded BinWalk. And I'm just going to take a look at one of these captures we took earlier. Camera 1, why not? And we'll BinWalk, and that should show us a file structure of the binary that we captured. Okay, there's a lot going on there. We can see once again Linux, it's ARM architecture, it's uncompressed. There's a kernel image, and there's some compressed data, and there's a boot header. I'm not for some reason. We know from the startup script that ran when we booted the camera that there's 4 partitions, being the bootloader, the root file system, and the 2 JFS2 file systems. We would expect to see those 4 partitions if we run BinWalk or something, but for whatever reason, there's just a couple of funnies with this, and I don't know, maybe we captured that. When we captured the download from the memory chip, it hadn't powered down correctly or something, and there were still files being written. But it is giving us something, and we're just going to go ahead and E for extract, and we'll extract that file. Okay, I'm just going to go ahead and close the terminal for a while. I'll open up the folder. Okay, we can see this camera extracted folder. So this is what Binwalk has created. And if we open this, we should see all the files that Binwalk has extracted. And man, there's a lot going on there. Okay, I know from just having to play around that this Squash FS file system, this is the Squash file system, and JFFS2 file system. These are two JFS file systems, are two partitions that our bootloader showed. And if we go on there, I'll just check there's actually files in here. Yeah, okay, so these are two JFFS2 folders, partitions, and these are Squash FS partition. All the rest really is superfluous for us at the moment. So I'm just going to go ahead and delete. So this is what I really need. These two folders here. What I'm going to do is just chuck them on a memory stick and transfer them straight over to my Mac. It'll be a lot easier to work on. Copy, and I'm just going to chuck them in this folder, this empty folder. Cool. Okay, what I'm going to use is, if I can find it, brackets. Yep, and I've opened folder is just that web folder where I've just chucked them, and it's already got the trees in there and semi-expanded them. So remember, these are the two folders straight off our binary image or capture that we got. And what I'm going to do is load up this index homepage, and I'm just going to go through and start looking at things, get a feel for how it works, and see anything related to a password or a login or changing credentials, adding credentials, that sort of stuff. Is definitely very going to be handy. Maybe if I go like that, and I can actually go live preview. Okay, so it's missing some links, or some of the linking structure is not quite right, but it's kind of what we'd expect to see once we log into the server. So configuration, cannot get system. Okay, I'm just gonna scroll down here. Configuration. Okay, I'm just gonna fix up. I mean, you'd be here all day trying to fix these links. I'm just gonna try and do the bare minimum that I need to load the page a little bit more. Where am I? www index and include. Yep, you're just gonna be one folder down. Okay, so system, we're in the system HTML. What else we got here? Yeah, I can maybe fix up a couple of these. Right, once again, I mean, I don't want to go through everything. I just want bare minimum that's gonna lead us somewhere. Anyway, let's have a look at this. Security, user account. So that looks interesting. And it looks like on mouse select or mouse select, setup security, security.html. So it's user account links to security. So I'm going to have a look down in security. Cannot get set up. Let's check some links in. Yeah. Security, user account. Show. Okay, here. So this looks interesting. This looks like where we enter a password or we set up a new user. Obviously it hasn't loaded because there's a lot of JavaScript references, links missing. But if we see here, existing, confirm user password, username, looks like we can add a user. And the user password will be this box here. And we can see input type is password, name, user pass. So somewhere there is this variable user pass, and that is the password for a given user. Yeah, user pass. And type of user, we have an admin, operator, or view. So it looks like we want to set up a new user password, and they want to be probably an admin. But where do we actually do that? Here we go. So this whole tab, or this whole box, is running method post. So it's getting information and it is posting it to this file here. This whole tab sends information back to this file, and that is a CGI or a common gateway interface. It's just a means of running a script or a common gateway interface. It runs a script back on the server over HTTP. So someone will enter data, it will go back to the script, it will run the script on the server, and then the output of that program or that script will go back to HTTP and send information back to their web browser. But if we go and have a look at this folder file, and we'll have a look at this actual file, so it is, it's actually back up here, in the user share www admin and edit account. Okay, so here we go. It looks like it takes information from this web page and passes it to this script. Yeah, and we can see there username and probably user pass. So that password they entered, that's stored in that variable, and their name is that variable. And it looks like it's passing these variables to a program called account manager. And if we look up here, we can see account mgr equals that their account mgr under user Espen. Okay, and that is an executable, which will only run on an ARM architecture. But if we just jump back again once, back to our edit script, edit account, we can see it calls this executable account mgr, which equals that string there. And if we have a look, we've got add, delete, edit. Now, probably the easiest one at this point is edit. And it looks like if someone is editing a username, then here we go. If they're editing a privilege, it'll run that script. And if they're editing a password, it will run that script. So it will run the executable, and those are the arguments there. So what we're going to do is jump back onto our Pi, and I'll just load up the camera again. And I'm just going to log in with the password I already saved. Yep, if you want to know BusyBox commands, I just type in BusyBox. And yeah, you got your version, a whole lot of commands that are built in for this configuration anyway. But back to where we were, we want to find this file, user Espen account manager, and that will be under cd/user and yep, we do have that program there, account mgr. Okay, it does nothing on its own, but what we're going to do is pass these arguments to it. So -e password, -n username, and I'll edit the root account, and -x password, so I will give it a new password. Cool, and we'll see there Vivo encode, so it's probably safe to assume that's VivoTech encoding, so it's got its own proprietary hashing algorithm, and that's the hash, and it's actually automatically saved it, and we can see that if we jump back to, so we'll just go to this folder here, and if you look at that hash, GAB, yep, GAB. So we have edited this root account for the web browser, and I'll just exit out of there, and really that is about it. what I'm going to do is I'll just reset this, make sure it's saved. Yep, we'll let that reboot again. And we'll jump across. Not quite. And we'll try the password we just modified. Yep, and we have access, and that is the home screen. It's a bit older now, and I mean, generally Macs don't support a lot of IP camera plugins. But the key thing here is we can get to this menu, and we can change a few settings. We can go to network, we can set up our wireless, we can change all this, we can chuck it on our Wi-Fi, we can add new users. We can put someone else in there if we want. We can have a look around. Yeah, we have full access. Okay, so lastly, now that we have access, how do we actually use this camera? Well, one of the easiest ways I've found is just VLC. And all I'm going to do is open VLC, and I'm just going to go open network. Yep, and I'm just going to type in RTSP / my username and password, which happens to be password, and enter my IP address, and no, wrong way around. Yeah, and there we go, and then we've opened a live stream to our camera. If you made it this far, congratulations. I don't know how many people are going to stick around for the whole video. Ended up being a bit longer than I thought. Making that PCB definitely threw a spanner in the works, but sometimes you just got to think outside the box, and got there in the end. So if you've got any embedded products lying around home, hopefully you've got a few skills now and your Raspberry Pi is set up in order to interrogate them. Thanks, bye.